So here we have an example where we'd like to take a look at the amount of current and voltage, amount of current and voltage that's going through each of the resistors here. Let's see if we can bring it back to that diagram here. We'll just leave it like this here. So we have a network of resistors with a battery, and we're interested in solving a problem here. We have a 10-volt battery. R1 shown here is 10 ohms. R2 is 3 ohms. R3 is 5 ohms, and R4 is 6 ohms. So we have different resistances. This is a more realistic kind of problem that we might encounter in the real world. And the problem originally asked what's the current through R3. We'll do that first, and then we'll figure out what the current through and the voltage drop across every resistor is. So I'm going to move to the camera for this portion, and then I will just draw a picture of this circuit. So we'll move to a camera view, and I'll start by drawing a picture of this circuit, and then we'll begin to solve it together. Here's my battery, here's my R1, here's my R2, R3, and R4. Very good, so there they are. Not perfect, but it's good enough. So that captures all the essence here. My R3, R4, R2, R1, and this voltage here, the EMF, is going to be equal to 10 volts here. So we could write that as a curly E if you'd like. And the goal is that we're trying to find the voltage drop across every resistor and the current through each resistor. That's our goal here. Let's start by thinking about how we can reduce this circuit. Well, R3, which is equal to 3 ohms, and R4, which is equal to, R3 is equal to 5 ohms. Let me just label everything here so we're nice and clear. R4 is equal to 6 ohms, R2 is equal to 3 ohms, and R1 is equal to 10 ohms. So you can actually already see kind of that the biggest voltage drop of them all is going to probably be through the R1 because it has the largest resistance, and we know that the voltage drop is proportional to current and resistance. So this will be one of the key equations that we use here. We can assume a direction of current, okay, something like this, and we're also going to have a junction which happens here. So if this is a current I going in, we can say that there's going to be an I1, or let's just call it I3 so we can stay really unambiguous here. That's the current that goes through I3. And then we can do an I4, which is the current that goes through R4. That's just why I chose those numbers here. And we'll just leave this one as I. So immediately we know from the junction rule that I is equal to I3 plus I4. And I want to emphasize that I just basically chose a random direction for those currents. The key point is that I chose the relationship between them. That's going to be from the Kirchhoff's junction rule. Okay. So the next thing that I'm going to do in the effort of figuring out what the current through R3 is that I'd like to reduce this network of resistors into kind of a single resistor. So you can see here that R3 and R4 are resistors in parallel with each other, which means that this circuit is equivalent to R1, R2, and this kind of R total here. This R total is going to be equal to 1 over R3 plus 1 over R4 inverse. That's the way that we sum up resistors that are in parallel. When I do that, I get 1 over 5 plus 1 over 6 inverse. You got to find a common denominator here. Looks to me like that's 6 over 30 plus 5 over 30 is inverse. And finally I can say that's 11 over 30 flipped is 30 over 11 ohms. So, well, that's probably somewhere around 3, a little bit less than 3 ohms. So in other words, now I have R1, R2, and this so-called R total, but it's the total for just R3 and R4. Sometimes you'll see this written as R3 in parallel with R4 is kind of one way of writing that, and that just means do this calculation, right? So the adding as the inverses. So in other words, if I wanted to figure out the real R total, right, so I'll say R completely total, right, so this is just RT, this is my real total here, that's going to be R1 plus R2 plus that original RT there. That's going to be 10 ohms plus 3 ohms plus my 30 over 11. We'll just make it into an actual decimal here. So open up a calculator real quick. Here's my calculator. I'll do 30 divided by 11. That's 2.7 plus 2.7. We're going to add these numbers all up together. It's 13 plus 2.7 is 15.7 ohms. That's my total amount of resistance here. Okay. So in other words, that behaves then as if we had a battery. Scoop this up a little bit here. As if we had a battery with one resistor. This is my kind of equivalent 10 volts, 15.7 ohms. And very easily I can see that there is a 10 volt drop across this resistor, which means that there's a current going through this effective total resistance of delta V divided by R total. So in other words, that's 10 volts divided by 15.7 ohms, and that's equal to, let's go ahead and get a calculator out, 10 divided by 15.7, that's 0.64. Yeah, okay. So we're going to have 0.64 amps. That's basically going through the whole circuit. So now, backing up, so this is my total current that's going through the battery. That means that in my case here, where I drew it as an I, right, that goes through this part of the circuit here, that is the same current that goes through R1, the same current that goes through R2, same current, and then the same current that goes through R3 and R4. So we have to get a little bit more sophisticated here in order to solve for the actual current that's going through R3 or R4. At this point, it would be easy to just say, well, I know what the voltage drop across R1 is. It's just I times R1, just 0.64 times 10, which would be 6.4 volts. We can do the same thing for R2. We do 0.64 amps times 3 ohms, and we would get the voltage drop across R2. Let's go ahead and try to figure out, though, how can we figure out the voltage drop across R3 and R4? Well, the answer is that we need more than just the Kirchhoff's junction rule. We actually also need to use Kirchhoff's voltage loop rule. You'll sometimes hear me refer to this as KVL. So in this case, we can pick a direction, go around a circle here, and make an equation that involves the things that we need. So for example, if I started right here and I go in a clockwise fashion, I can say that I have 10 volts minus the voltage drop across R1, minus the voltage drop across R2, and then since we're going in the same direction as this resistor here, that will be minus the voltage drop across R3. When we go over here, we get back to this dot where I started. That should be equal to 0. Filling in for the actual values, I can see that delta V1 is going to be I, that current that's going through this resistor, times R1. This is going to be I times the resistance of resistor 2. Now we get to be careful here because when we get to this R3, there isn't the current I going through it. It's actually the current I3 going through here. So we have I3 times R3. So finally, putting this all together, we can see that we have 10 volts is equal to IR1 plus IR2 plus I3 R3. So now I did solve for the current earlier, and that could be helpful to us. And this allows us to then solve for I3 and R3, but I'm going to show you an alternate way in a moment, which is that I could make a loop around here. Even though there's no battery in here, I could actually go voltage drop across R4 and the voltage gain across R3 going around in a circle, and it's going opposite direction of the current. It gives me another equation. That could give me an I3 and an I4 relationship. We'll do that in a moment, but first, let's take a look at how putting in the current here will allow us to solve for I3. Notice that we know the values of R1, R2, R3, and we know the current is 0.64 amps, but we don't know I3. Therefore, I'm going to rearrange this equation to solve for I3. 10 volts minus I times R1 plus R2 divided by R3 is equal to I3. If you can't do that one in your head, then just do it in a couple of lines. That's not a problem. This I is going to be 0.64 amps. This resistance is going to be 10 ohms. And this resistance here is going to be 3 ohms. R3 is going to be 5 ohms. So you can see that there are a lot of puzzle pieces that we're putting together in here. But if we stay organized, we find that we have all the numbers we need. Rearranging, I3 is equal to 10 minus 0.64 times 10 plus 3, which is 13, divided by 5. Looks like I'm going to need a calculator for that. 10 minus 0.64 times 13, and we're going to use parentheses here to make sure we don't make any mistakes, divided by 5 gives me 0.336. So we have 0.336 amps is our SI unit for current. That means the number of coulombs per second. So about a third of an amp. And finally, I'm going to show you another type of voltage loop rule, which is if I took this little dot right here and I moved around in a clockwise fashion, I'm going to see a voltage gain as I go in the opposite direction of current here. I'm going to see a voltage drop as I go in the direction of current across R4. So maybe I'll just pick another page here. Going around this loop, I can see that I have plus voltage drop across R3 minus the voltage difference across number 4 equals to 0. So why was the V3 plus? It's because we were going in the opposite direction of current. The V4 is being minus because we're going in the flow of current, so I4 flows down through here. Finally, we can see that V3 is equal to I3R3. V4 is equal to I4R4. Therefore, I3 times R3 is equal to I4 times R4. So you notice here, we basically have known now, but we don't know I4. So I4 is equal to I3 times R3 divided by R4. And so I3 is 0.336 amps times the resistance of R3, which is 5 ohms, and divided by the resistance of R4, which is 6 ohms. So it looks like we're going to have 5/6 of this value here, which, again, I'm just going to take this number here, our 0.336, I can just do answer, times 5, divided by 6. Looks like we have 0.28. So 0.28, and our unit is amps. Okay. So this is our I4. So let me summarize now what it is that we know and what it is that we don't know. We know that I1 is equal to I2, which is we call it just as I. That one was, if you look back here, was 0.64 amps. I3 we found to be 0.336 amps. And I4 we found to be 0.28 amps. So we have basically all the currents. We have the currents going through things. If you wanted to find the voltage drop across R1, this is just I1 times R1. So in that case, it's just the regular I, which is 0.64, because this is in series with the battery here, times the resistance, which is 10 ohms. And as promised, that is 6.4 volts. Delta V2, the voltage drop across resistor number 2, it's going to be I2 times R2. That is going to be also 0.64 amps times the resistance value, which is 3 ohms. Looks like I'll need a calculator. .64 multiplied by 3, 1.92. Okay, sorry I had slid it off the screen there for a moment. So here's kind of our summary. If we want to find the voltage drop across R3, which is, I guess, what originally the problem was asking, but we're going the full way here. I3 is 0.336, so 0.336 amps times the resistance value of R3. That value was 5 ohms. So 5 ohms. And when we multiply those two together, I'm going to do 0.336 times 5, and I get 1.68 volts. Finally, we're going to take the voltage drop across R4, and before we even do that, so it's going to be I4 times R4. Before we even do that, I want you to notice something here, is that the voltage drop between this dot here and this dot here should be the same as between here and here. In other words, because R3 and R4 are in parallel, that means that the voltage drop across R3 should be the same as the voltage drop across R4. So if that's true, doing this one should actually yield the same result, that I4, which is 0.28 amps, even though it has a different current going through it, going through the 6 ohm resistor is going to yield 0.28 times 6. It's also 1.68 volts, just as we had expected from knowing that those were two resistors in parallel. So we've solved for everything. And then finally, I'll share one more thing, which is that given this information, if we wanted to figure out the amount of power dissipated through any of these resistors, so why don't we just say the power dissipated through R3, all we would have to do is say power is equal to I3 times delta V of 3. So I3 in this case would be 0.336 amps, and voltage 3 would be 1.68 volts. Remember that the amp times the volt is a definition of a watt. 0.336 times 1.68. And finally we're left with a number which is 0.565 watts. So half a watt basically. I believe that you can now do the remainder of the resistors, so I'd like to encourage you as an exercise to figure out the power dissipated through R1, R2, and R4. The other thing you could do is you can notice that if we were to trace around the voltage gain of 10 volts minus the 6.4 minus the 1.2 and then minus the 1.68, you'll actually find that we get to 0 again. That's going to be a confirmation. You can always confirm the voltage loop law. In other words, here was our voltage loop rule. You can confirm this now by plugging back in these numbers and check to make sure that this is indeed 0. The other thing that you could do is you could actually ask yourself the question, well, how much work does the whole battery have to do? Well, the whole battery is supplying 0.64 amps. Of course, that does get divided once you get to R3 and R4, but if you're talking about the current that's going through the battery, the power supplied by the battery is this I times its voltage, right? So in other words, it looks like 0.64 multiplied by 10 volts is giving you 6.4 watts. Another way you can do this, so this would be delta V of the battery multiplied by the total current. And that looks like it's going to be, well, here, I'll just write it out here just for clarity's sake. 10 volts is our voltage battery, and I is 0.64 amps. So you can see that putting those together gives you 6.4 watts. Another way of writing that would be to look at this equivalent circuit here and say, well, I know that also I could write it as I squared R. So in other words, I being 0.64 squared it and multiplied by 15.7 ohms, we should end up getting the same result. So 0.64 squared, I'll just do times 0.64, times 15.7 ohms gives me also 6.4. And that I'm just rounding here because, of course, I've rounded a couple of numbers, so I'm going to be off by just a touch. If you need more precision, keep more digits. So the point that I wanted to make is that any of these calculations will work if you know the current that's going through a resistor and you know the resistance value, or if you know the voltage drop. You can also use, remember that we have sort of three formula, right? Delta V times I, or delta V squared divided by R, or I squared times R. All three of those things are sort of equivalent ways of looking at a problem. And so if you are trying to find the power dissipated through any one of the resistors, as long as you know the current that's going through the resistor and that resistance value, you'll get the same result as if you knew the voltage drop across that resistor, square it and divide by the resistance. Or in our case, what we did is looking at the voltage drop and the current going through the resistor, and we should get the same result in all three of those cases. If you feel comfortable to calculate the current through each resistor, the voltage drop across each resistor, and the power dissipated by each resistor, then you've just accomplished a major goal for our section around DC circuits. A great way to practice your knowledge is to use the FET simulation. So for example, if you type in FET circuits, you can actually practice making a circuit, and you can test out your ideas. So I'll make a new tab here and just bring this over briefly and just remind you that you can type in FET circuits, and the very first link that comes up, the DC construction kit, will allow you to begin to make your own circuit. So for example, by placing a resistor, by placing some wires, you can now begin to make your own circuit. And so here I'll just make a very simple circuit here of two resistors that are in series with a battery. So you can see now the flow of electrons. You can use the voltmeter, you can use the ammeter. Keep in mind that you'll have to break the circuit in order to be able to measure the current going through the battery. You can also click on any of the resistors and figure out what that resistance value is, and based on that you can begin to measure the voltage drop across one of the resistors here. And if I click on this, for example, and I change the resistance to a higher value, you can see that there's more voltage drop that's across that resistor. So I encourage you to play with this, try making up a circuit, and then see if you can predict what voltage drop is going to be, or what the current will be for this circuit. And when you check and you make sure that you're right, and that will confirm that you're consistently applying the theory to an actual a simulation of an experiment. And this would be the same as an experiment that you would do in real life in the lab, that you would be getting exactly those same results. Thank you for watching, and I hope that was helpful. Please practice with the FET simulation, and also there are many problems to work in the back of the text. Keep practicing them until you feel comfortable finding the voltage drop across a resistor, the current through a resistor, and the power dissipated through a resistor, and also the amount of total current that's going through your circuit and the total power that's being provided by your battery.